At the beginning of any formal study of the types of chemical reactions, it's important for us to see just how chemistry affects our world. And the answer is chemistry, done for the right purposes and in the hands of responsible people, makes the world better. So this is a short introduction to stoichiometry, measuring, understanding, engineering. There are three big questions that we must ask when we are studying stoichiometry. The first is we need to identify what is reacting. The second, how are the chemicals reacting? What is happening down on the molecular and ionic levels? And finally, and this is of course the whole goal of stoichiometry, we want to know how much reactant forms how much product. This is a way that we can begin to control our chemical reactions, and for instance in engineering, it's the way we determine costing so that a chemical engineer can get the most product for the least expense. Let's talk about what's reacting. We know that hydrogen and oxygen react. They burn, and hydrogen and oxygen reacting, for instance, powers a number of rocket engines. However, hydrogen can be made to combine with oxygen in what's called a fuel cell to produce an electric current rather than heat. You can see here that air comes into the fuel cell, and oxygen, of course, is in air. Hydrogen is provided, and in this process that involves an electrolyte, the hydrogen, which is a reducing agent, hydrogen is oxidized and it gives off electrons. The oxygen takes the electrons. The hydrogen and oxygen then combine to form water, and water is taken out of the fuel cell. The electrons are made to flow through a circuit before they get to the oxygen, and that's how they can produce an electric current. At this point, California, for instance, is mandating certain emissions controls, and the hydrogen-oxygen fuel cell is being used by a number of companies to make that happen. Let's talk about oxides reacting. Useful metals and nonmetals and chemical compounds can be taken from mined ores. For instance, iron 3 oxide, Fe2O3, is one of the principal components of ores that are mined in certain areas of the world. Here you see a modern blast furnace is being used to combine with carbon. The carbon takes away the oxygen in an oxidation-reduction reaction, and molten iron comes out of the blast furnace. Another question of what reacts. Small biochemicals can be put together in biological systems. They react together to form large ones. These are always catalyzed by enzymes. You studied that in biology. Biochemistry studies how these small biochemicals are coming together to form large biochemicals which are used in the body. Proteins, for instance, DNA is another type of substance, RNA. All of these larger molecules are put together from smaller ones, and research is done to control that. Also, large biochemicals, like the glucose that you take in your body and fats, react to form small ones. These large molecules tend to be high-energy molecules, and in the process of being taken apart, they can be made to yield up their energy in the form, as you see here, of ATP coming out of the large molecules in the mitochondria. Again, once more, we have the need for enzymes to make this happen. The second big question that we ask in chemistry is, how do chemicals react? And there's really two things that can happen besides just heating something and shaking it apart as you did in your decomposition of a hydrated crystal. The two things that we look for are, first of all, ions moving. We call these ion swaps. Some call them double replacement reactions. These are reactions in water between two ionic substances. One type is the acid and base reaction. As you know, acids, which give off hydrogen ions, and bases, which give off hydroxide ions, will react together to form salt and water. The salt still remains in solution. The water, made from the hydrogen that came from the acid and the hydroxide ion that came from the base, the water does not break up. The other thing that we can see in an ion swap is a precipitation reaction, where we have two ionic salts that are soluble. They react to form a slightly soluble or insoluble salt. The example that you may recall is the formation of lead iodide. The second thing that happens in other chemical reaction is electrons move. So either ions are moving or electrons are moving. And in an electron move reaction, we call that an oxidation-reduction. Short for that is redox. Instead of oxidation-reduction, we just say redox. So for example, aluminum ore can be taken apart with the proper electrolytic process to form molten aluminum, and the aluminum then can be pressed into sheets, aluminum foil, or used for all kinds of purposes. This, of course, requires electricity, but it is an oxidation-reduction reaction because the aluminum ions in the reactant, the original reactant, the aluminum ions are gaining electrons that are supplied maybe from an external source, like a power plant, and they turn into aluminum atoms, aluminum metal. This is run at a high temperature, which is why molten aluminum comes off. You'll notice this is spelled in the European fashion as aluminium. Another oxidation-reduction reaction that does exist the opposite, that produces electricity, is an oxidation reduction that happens in your lithium battery, in your cell phone, or in other devices. High energy metals and salts will react, and they will give off electrons that can run the various electronic devices that we have. Here's another redox type reaction. Water and carbon dioxide can react with sunlight being provided, and that can produce high energy molecules. Now, you're used to having this happen in photosynthesis, which you studied in biology. But now, with our desire for more green electricity, solar energy is being used by many researchers in order to break up water into its component parts, and you can get hydrogen out of it. Here's one that produces, from carbon dioxide, produces carbon monoxide, which is a burnable fuel. Of course, it's also dangerous, so you have to take care if you're doing something like this. So it's possible to use oxidation-reduction reactions to produce fuel. The last question, the last big question we ask in stoichiometry and studying reactions, is how much reactant forms how much product. So for instance, researchers want to know how much of a chemotherapy drug that they can give to kill a cancerous tumor without killing the cells around the cancerous tumor. And that's a stoichiometry question. More to the point, something that affects everybody is the big fracking fields in the northern part of our country and in Texas, those fracking fields are producing oil and gas out of shale, and they use chemicals to get it out. So you have to ask the question, how much fracking chemical do you have to use to extract petroleum without bankrupting the oil company or harming the environment? So here is a type of illustration for that. What additives are necessary and how much water and sand are necessary, and they are constantly analyzing these things. Chemical engineers analyze these things and constantly trying to improve the quality of what they're getting out and reduce the expense of getting it out, and that expense includes environmental waste. We talked about a blast furnace. Chemical engineers have to go in and study the process so that they can determine how much carbon to use to make the steel, how much oxygen is necessary in order to make the carbon start burning so that it can reduce the iron ions to iron. And so we have seen the three big questions, and those are questions you will study.